Problem 5-20 is one that we did in class, and it combines aspects of both a transportation problem and a fixed charge problem. We have 5 different plants that are producing vehicles and being transported to warehouses, and we have a table that gives us the cost for movement for each vehicle. We have supply at the plants, and we have demand at the warehouses. And for a transportation problem, we would typically use decision variable Xij representing, in this case, the number of cars that are built in plant I then shipped to warehouse J. The second part of this problem comes in how do we incorporate these fixed charges and how do we make a decision of which plants to remain open, which ones to close. So that is the fixed charge part of this problem. Decision variables for the problem. Xij, again, we've discussed that. Decision variable yi will represent the decision to keep plant I open. And that will be a binary variable that's going to take on a value of 1 if we keep the plant open, 0 if we don't. The objective function for this problem, well, we've got costs that are associated with movements, and we have costs that are associated with keeping the plants open. So we're going to take those costs together as our objective function. We're going to minimize cost, and that objective function is going to be the minimum of the sum of the product of the decision variables x and the cost of movement, plus the sum of decision variable y and the cost to keep the plant open. Looking at that in shorthand notation, well, longhand notation, just looking at plant 1, 56x1a, 21x1b, 31x1c, and 65x1d. The cost to ship from plant 1 to each of the 4 warehouses times the number of vehicles that are going, plus the decision to keep plant 1 open, y1, times the cost on an annual basis of keeping plant 1 open. So we've got both the x decision variables and the y decision variables in here. I'm showing you 5 terms. We have 5 different plants, so the objective function would have a total of 25 different elements in it. Again, just looking at the first plant for simplicity's sake. Demand at warehouse B. As a transportation problem, we do have demand. Warehouse B, the demand is 14,000. And we need to meet or exceed demand, so our relationship is going to be a greater than equal to. What's going to warehouse 1B? Well, X1B, the cars that are going from plant 1 to warehouse B, plus X2B, plus X3B, plus X4B, plus X5B. On the supply side, we have 12,000 cars at plant 1, and we cannot go over that, so that relationship is going to be a less than equal to what cars are going from plant 1? X1A, X1B, X1C, and X1D. All of the cars that are going from plant 1 to the 4 different warehouses. They have to be less than or equal to 12,000. But again, this is a fixed charge problem. We don't know whether we're going to keep plant 1 open or not, so this capacity is not really complete. We only have capacity of 12,000 at plant 1 if we keep it open. If we close plant 1, capacity goes to 0. So we need to adjust the right-hand side of this to take that into account, and the way that we do that is by multiplying that supply by decision variable y1, the decision to keep plant 1 open. Now if y1 takes on a value of 1, the right-hand side is going to be 12,000. If we decide to close plant 1, y1 goes to 0, right-hand side goes to 0, and at that point we can't ship any cars. Now this is very similar to the traditional fixed charge problem with the linking constraint. In fact, this is the linking constraint. It links the x decision variables with the y decision variable. The general form of a linking constraint is x sub I minus big M y sub I less than or equal to 0. In that linking constraint, x is going to be a variable that can take on any particular value. It might be 0, it might be 1, it might be 100. Y is the binary decision variable. It takes on a value of 0 or 1. Without this big M in here, this constraint would artificially limit the x decision variable to 0 or 1. X could only be 1 if y was 1, could be 0 or 1 if y was 1, but it can't be any larger than that. By incorporating big M, we allow x to be as large as M. So M is setting an upper limit on how big x can be. In this particular problem, we don't have a big M, or at least a big M is not showing. This 12,000 acts as big M. It represents the largest value that all of these x decision variables can take. It's the capacity of plant 1. We cannot ship any more cars from plant 1 than we have capacity. Rewriting this as a traditional linking constraint, well, what we've got to do is move this 12,000 y1 to the left-hand side, so minus 12,000 y1 less than or equal to 0. And you can see now that this follows the general form x sub 1 minus big M y sub 1 less than or equal to 0, the linking constraint. Final constraints for this problem: all of the decision variables x sub I or xij have to be greater than or equal to 0, and the y decision variables have to be binary.